Chapter 2 Measures of Location. In this chapter, we will deal with three main measures that provide descriptive information about a dataset in a single number. By now, you're probably familiar with the term average. If an entrepreneur wanted to know which items in a product range were selling well or selling poorly, the first piece of information he or she would probably ask for would be the average number of sales per day for each item. This single number would provide a useful description of where the number of sales per item were located relative to each other. In other words, which items over a long period of time sold well or sold poorly, smoothing out the ups and downs of each particular day. The average could also provide an entrepreneur with a benchmark for how sales performed on subsequent days. In other words, there were more or fewer sales than usual on a given day. The average, also known as the mean, is referred to as a measure of location. There are other measures of location that can be used instead of the mean. These are the median and the mode. These measures of location give us a rough idea of where we would expect an observation of an experiment to lie. In other words, how we would roughly expect an experiment to behave. We will present three measures of location in this chapter: the median, the mean, and then the mode. The median. To calculate the median, one would first need to arrange all of the observations in a dataset in ascending order, in other words, from smallest to largest. The median would then be the middle observation. In other words, the median would be the observation which would have an equal number of observations above and below it. Example A. Calculate the median price quotation received from a list of bidders for their hourly wage rate, dollars per hour. Here we have two datasets, Project A and Project B, where we have received price quotations for the dollar per hour wage rates from various service providers. Solution. Project A. We first need to rewrite the observations in ascending order. This yields 25 being the smallest, and then 30, and then 45, and so on, all the way up to 120 being the largest observation. There are 11 observations in total for this dataset. The median must therefore be the sixth observation from either the right or the left, when these observations are ordered from smallest to largest. Choosing the sixth observation as the median would ensure that there would be 5 observations larger than the median and 5 observations smaller than the median. The median quote received is therefore 65, which is the sixth observation. As a general rule, if a dataset has an odd number of observations, the median would just be the ith observation, where I is just a general number given by the formula n plus 1 divided by 2, where n denotes the total number of observations in the dataset. So in the case of the dataset above, I is equal to 11 plus 1 divided by 2, because n in this case was 11 observations. So we take 11 plus 1 divided by 2, and that gives us 6. So the median would be the sixth observation when the observations are ordered from smallest to largest. The sixth observation was 65. Hence, the median wage rate quotation would be $65 per hour. Project B. For this example, we again write the observations in ascending order, and this yields 30 being the smallest, and then 40, then 45, then 50, all the way up to 125 being the largest. This time, however, there are an even number of observations in the dataset, so there are 14 observations in total, which is an even number. We therefore cannot apply the formula that we saw in the previous question. When there are an even number of observations in a dataset, we instead take the median to be the average of the n over 2 and the n over 2 plus 1 observation. Again, n here refers to the total number of observations in our dataset. So we would need to find the average of the 14 divided by 2. Here n is equal to 14. So that would be the seventh. And then n over 2 plus 1 gives us 8. which would be the 8th observation. So we take the average of the 7th and the 8th observation to calculate our median. So we would need to find the average of the n divided by 2, and n, remember, in this case is 14. So we take 14 divided by 2, which gives you 7. So we take the average of the 7th, and n divided by 2 plus 1, which gives you 14 divided by 2 plus 1 is 8. So we take the average of the 7th and the 8th observation. And these observations are 65 and 70 respectively. Taking the average of those two gives you 67.5. So here the median is 67.5. In this case, the median can be thought of as being a value in between the 7th and the 8th observations. The median thus has the same number of observations above it, 7, as the number of observations below it, 7 observations. Calculating the median from a frequency table. A frequency table lists observations as well as their corresponding frequencies. Unlike a grouped frequency table, a frequency table lists the exact values that the observations took, and not a range into which they fell. The calculation of the median from such a table will be shown by means of an example. Example B. Let's imagine a customer satisfaction survey can only take on one of 5 values: 1 star, 2 stars, 3, 4, or 5 stars. We would like to know what the median rating for a customer satisfaction survey was. A frequency table of the feedback received from 500 customers is shown below. In this table, we had, for instance, 23 of the 500 customers gave the company a 1-star rating, 52 out of the 500 customers gave a 2-star rating, 175 gave a 3-star rating, 200 gave a 4-star rating, and 50 gave a 5-star rating. And right next to that, we just have the cumulative frequency, which shows 23 customers giving a 1-star rating, 75 customers giving at most a 2-star rating, so 75 customers giving 2 or 1 stars, 250 customers giving 3, 2, or 1 stars, and so on until 500 customers, which was our complete data set, giving at most 5 stars or less. Firstly, we should notice that this table is just a compact way to write out all of the results of each of the 500 surveys completed. No important data has been lost here. The table here is a frequency table, unlike a grouped frequency table. For a grouped frequency table, we would lose much of the data, as we would not be able to determine the exact rating of each of the surveys received. If, for example, the rating buckets were less than 3 stars and more than 3 stars. In other words, the different results were grouped together into larger categories. For a grouped frequency table, we would then only be able to estimate the median within a certain degree of accuracy, and this would depend on how big the different groups or buckets were. And we'll see this in the next section. A second point to note is that in its current form, the table gives all the survey results in ascending order, 1 star all the way to 5 stars. Recall that when we calculate the median, we need to order all of the observations in ascending order. Since the table in its current form already does this for us, we can just observe the cumulative frequency column to find the median observation. Since the number of results of the survey, 500, is an even number, the median would be the average of the n divided by 2 and the n divided by 2 plus 1 observations. So averaging the n over 2, which is the 500 divided by 2, or the 250th observation, which was 3 stars, and the 251st observation, which was 4 stars, yields 3 star plus 4 star divided by 2, giving you a median of 3.5 stars. Thus, the median customer satisfaction rating here would be 3.5 stars. So just an important point to note that even if 3.5 stars was not on the survey itself, the median is just the number that represents the observation whereby an equal number of observations would be below that value and above that value. So even if we didn't have a rating category of 3.5 stars, the median is 3.5 stars by virtue of its calculation. Calculating the median from a grouped frequency table. The only way to calculate the median from a grouped frequency table is by constructing a cumulative frequency curve. Suppose a light bulb manufacturer wanted to evaluate the median time taken for a light bulb to burn out in order to correctly market his light bulbs as longer lasting. The manufacturer took a sample of 1,000 light bulbs, kept them switched on until they burnt out, and recorded the number of light bulbs that burnt out at certain time intervals. So in our table, we record the number of light bulbs that burnt out versus certain time intervals. So in the first 50 hours, with x being our random variable, the number of hours taken for a light bulb to burn out, we see that in the first 50 hours, 10 of the light bulbs burned out. In the next 50 hours, in other words, after hour 50, between hour 50 and hour 100, we had 115 different light bulbs burn out. In the next 50 hours, we had 125 light bulbs burn out, and so on until the last 50-hour interval, which took them from hour 250 to hour 300, where we had the last of the remaining 25 light bulbs burn out. So in total, looking at the cumulative frequency, you had 10 light bulbs burn out within 50 hours. You would then have the initial 10 plus the next 115, giving you a cumulative frequency of 125 light bulbs, which would burn out at 100 hours or less. And then in the next column, you'd have 250 light bulbs in total, which would burn out at 150 hours or less, going all the way up to the 300th hour mark, where all 1,000 light bulbs would have been burnt out. The resulting cumulative frequency curve is shown below. To find the median, we don't need to concern ourselves about whether the total number of data points is odd or even. All we need to do is find the n divided by 2 observation. So in this case, we had 1,000 observations. Divide that by 2 gives us 500. So we just need to find the 500th observation. In order to do this, we draw a line from the point 500 on our y-axis. Remember, we plot cumulative frequency on our y-axis. And we find the point 500 on our y-axis, and we read off the corresponding x-axis value. And on our x-axis is hours. So the median life of a light bulb is therefore approximately 165 hours. The light bulb manufacturer can therefore market his light bulbs as lasting as long as 165 hours. As we said earlier, whether the number of observations is even or odd does not matter. If, for instance, we only recorded 999 light bulbs in our dataset, the median would be found by reading off the value 999 divided by 2, or 499.5, on our y-axis, and then finding the corresponding x-axis value for hours. The calculation of the median takes one observation, in the case of a grouped frequency table, or at most 2 observations, in the case of a frequency table, into account in its calculation. And it disregards all of the rest of the observations. This seems to be somewhat a waste of information. However, this fact does have an advantage to it. The median tends not to be affected by extremely small or extremely large observations that may distort the true picture of how a random variable behaves. For example, if we had a dataset that recorded the annual percentage gains or losses on a particular share on the stock market, the observation minus 80% is an extreme value here, which, if taken into account, could distort our perception of how the share would actually behave in the long term. This observation could have been triggered by a massive market anomaly or a rare once-off event, and should not affect how an investor would perceive the behavior of the share in a normal world. By looking at the median, this negative 80% move in the share price would be disregarded and would not affect our measure of location, which would tell us how we would expect the share to behave on an ordinary day. Extreme observations, such as the negative 80% seen above, are commonly referred to as outliers.